Hello everyone, my name is Sai Kumar Reddy Palnati. I am going to present my project on reinforcement learning based cost and latency optimization in Kubernetes enabled multi-cloud environments. This is my final presentation and I will walk you through the key aspects of my research. So first, we will start with an introduction to set the stage and then followed by the literature review to see what's already out there. Then I will define the research problem and explain my methodology and then design, and I will share the evaluation approach as well, and then I will highlight the main outcomes, and then I will wrap up with conclusions and future work. This should give you the complete picture of my work. And then let's talk why it matters multi-cloud environments in different organizations, like combining AWS and Azure gives us incredible flexibility for running Kubernetes workloads, but there will be some big challenges, especially in optimizing costs and latency. The def- the default Kubernetes scheduler does not dynamically do all the things for vendor specific pricing or network latency between the clouds, which can lead to insufficient and which they think to 20 to 50% higher costs in real world setups. Like with the global cloud spending almost hit at to $600 billion in 2025. So by using the reinforcement learning, we can automate smart pod placement decisions, could save a ton of money and improve performance. By provide focus on building an RL scheduler to tackle exactly this thing. And you can see here was the spread of cloud market in today's world. And moving to the literature review, I surveyed existing work across several areas in AI for cloud scheduling. Kumari and Mishra in 2025 proposed a weighted A3C approach for solution allocation for the resource allocation, but it's not native to Kubernetes. For Kubernetes specific scheduling, Wang et al. In 2022 used Q-learning, but it struggles with dimensional inputs like multiple metrics. But in multi-cloud orchestration, Chen et al. In 2022 applied a simulated approach, but it is a rule-based and not adaptive to changing conditions. But finally, on cost and latency optimization, studies like Sharma in 2024 and Liu in 2023 focus on just one objective, either cost or latency, but not both together. The gap is clear. No one has built a RL system that jointly optimizes cost and latency in Kubernetes multi-cloud setup. So that's where my work fills in. And yeah, so the research problem boils to this, like and our research problem is how we can create an intelligent and adaptive uh, scheduler for Kubernetes that minimizes both cost and latency across multiple clouds. Now here I'm taking AWS and Azure in my case. So for methodology and tools, I used Kubernetes with Minikube for local testing, then scaled in real AWS EKS and Azure EKS clusters. Monitoring was handled with Prometheus and Grafana. The core RL agent was built in Python using Ray RLib with the PPO algorithm. I also used Docker, Helium, and kubectl for deployments. Data came from public cloud pricing APIs, and the synthetic workloads are generated with Locust. It's a tool, and latency traces from pinging between the regions. So here the here is a system architecture. It shows how the RL agent integrates with Kubernetes. The agent observes the state, decides actions, and get rewards based on outcomes. The design, I choose PPO because it's stable and handles continuous state spaces well, and the state includes normalized values for cost, latency, CPU, memory, and workload type. Actions are simple, like just we have to place the pod on Azure or AWS. The reward is negative weighted sum minus alpha times cost minus beta times latency, turning into a multi-objective optimization. Everything runs on lib for efficient training. And here you see how the RL agent has been designed. And then for evaluation, I compared against baselines, the default Kubernetes scheduler and the static aware rule-based one. Key metrics were total infrastructure costs in dollars, average pod to service latency in milliseconds, and scheduling efficiency via node utilization percentage. I tested on batch jobs and other synthetic workloads to stimulate real scenarios. And the main outcomes were like I successfully set up a multi-cloud Kubernetes environment with AWS and Azure. The custom RL scheduler prototype is implemented and functional, trained on a mix of synthetic and real pricing and latency data. So based on simulations and literature benchmarks, I expect 20 to 30% cost reductions and 15 to 25% latency improvements compared to the default scheduler. And yeah, and coming to the conclusion part. In conclusion, I developed a RL scheduler that achieves about 75% optimization in multi-cloud Kubernetes using real-world AWS and Azure data. This proves RL can be seamlessly integrated into Kubernetes for intelligent real-time decisions. Jointly optimizing cost and latency is not only possible but leads to significant values and performance gains for cloud-native apps. And for the future work, I would like to train on real production workloads, extend to more providers like GCP or Oracle, and I and we can add energy efficiency as a third objective, and maybe open source it as a Kubernetes extension, exploring other RL variants like SAC, or could push it further, right? And these are the references. And thank you.